Hi everyone, I am Xingyi Chen.
Hi, I am Jingxian Xu.
Today we're going to talk about our research on label representations and modeling classification as text generation. We conducted this research with Alex Wang. And this is our outline. We will cover first our topic and motivation, second, our hypothesis and methods, and third, our results and analysis. Our project uses T5 as a typical sequence-to-sequence model, which models classification tasks as text generation. This is a graph provided in T5's paper. On the left are the pre-processed inputs and the targets. On the right, which are also the labels, are represented as strings for the model to generate. This formulation raises the question of the best string to represent the label, or if the labels need to be represented with task-related strings at all. We will explore both questions and give our analysis. We experiment with T5, specifically the T5 base model. See this table for our input and output examples. Among the 4 datasets, PAUSE is the only dataset that has not been pre-trained on by T5. So for COLA, SST2, and COBA, we format each example the same as is formatted by T5. For PAUSE, because it is the same task as MRPC, a task that has been pre-trained on by T5, we format the examples identically to how T5 processed MRPC. Our hypothesis is that different labels perform differently for a specific task. Also, task-related labels should perform the best. One important part of our method is about generating the labels. For each dataset, we try the original label and also the reversed original label. We then tried randomly generated strings as labels to see whether the labels need to make semantic meanings at all. We also tried task-unrelated strings, including antonyms, synonyms, relevant strings, and irrelevant strings. Finally, we tried task-related labels, including both matched labels and reverse labels. We take SST2 from glue as an example. The process target is positive or negative. The labels we tried are yes or no, and no or yes.
Here are the parameters we used for optimization. For all datasets, we evaluate the accuracy of the development set for every 200 steps and report the best accuracy. Previous studies found significant differences in performance with distinct data sizes. We also run 4 tasks in lower data regimes. For each dataset and setting, we evaluate 3 rounds with different random seeds. For SST2, we get similar results for all choices of label representation. For COPA, we observe notable performance differences between various labels. For COLA and PAUSE, the performances we get using different labels vary, but by no more than 2%. In the low data setting, label representations sometimes have an impact on the overall performance. For PAUSE, label representations do not matter that much for both low data settings. For COLA with a 400 training set size, the difference of label performance is more noticeable. We obtain a result with matched label representations performing the best and reversed ones doing the worst, suggesting that the label representations might not matter that much, as long as we do not pick labels that flip the class definition. For SST2, label representation represents a minor impact on performance of low data setting, which is likely due to the large amount of pre-training in T5 model. For COPA, label representation makes a difference to the performance, while matched labels performing the best and random labels showing a high variability. In the extremely low data settings, differences between labels become more significant and noticeable, with several label representations failing to learn the task and obtaining accuracy near chance. This is a summary of our findings. Thank you for listening.